special recourse structure, you don't even have to look, because the answer is always simple. Now, I could understand if this doesn't look like simple recourse to you, because simple recourse, you have this notion, then the recourse matrix is identity minus identity. Is it? What is the catch? That recourse matrix, identity minus identity, corresponds to the canonical formulation, having only equality constraints in the second stage. And this one has inequality constraints. Right? So part of the recourse matrix is hidden in the slack variables that we should include if we write it as equalities. So yes, this is simple recourse, and that immediately proves that it is complete, because we prove generically any simple recourse problem is complete. End of story. Okay? So that makes us happy. Let's continue. There's an important remark. In between the story about this particular model, I have a few slides on what they look like, what it looks like to implement this in software as a PIR. And this is to show you the whole collection of stochastic programming models that can be analyzed using this software. And the point is that what we just did, recognizing the particular recourse structure, is very important, because the software will use it to come up with suitable solution methods for this algorithm. So our knowledge indeed tells us, well, this is a multi-stage problem. In fact, it's a special case, namely two-stage. It is fixed recourse. We analyze and it's complete. In fact, it's simple, and it has continuous variables. So that's the class that it belongs to. And in software, you need to indicate it. It wouldn't be wrong to say this is an instance of fixed recourse. But then the issue is, of course, that the software doesn't know that it's actually a special case, so it will not propose to use the special purpose algorithms for that indeed very special case that we're dealing with. And so it's important for you to use your knowledge in using the software. Okay. Another slide is on how you specify such a model in SLP-IOR, and I guess most of the elements are not that relevant. The only remark is that it's just a funny thing in SLP-IOR. It will not allow you to formulate the model involving inequalities and then state it in simple recourse. It just only accepts equality constraints. Well, you know how to do that, but this is a word of warning. That's why in the specification the number of columns in the second stage is 4, whereas we have only 2 real variables in our formulation. The other 2 are slacks. Okay? The other things are, I think, not that relevant at this point, so we continue. This is the very nice overview of the capabilities of the software, and I hope that it's readable for all of you. And hopefully you recognize that all those buttons correspond to things we've been discussing already during this course. In particular, once you've entered the full specification of the model, you can do a number of things. One of them is to say, and that's the top left button, solve for me the expected value problem. An easy approximation using mean values for the random variables. That is, solve the corresponding LP. The other buttons are solve the wait and see problem. Well, solve the difficult problem, the recourse problem, and evaluate the expected result of the EV solution. Remember, that's how we get an upper bound for the true optimal value. It's all implemented in SLP-IOR, and you know enough to know what to do at these buttons. In fact, there's 2 more. One is to check complete recourse. We discussed that. There is this nice dual formulation, and that's behind that button. In fact, you can even press a button to check for you whether relevant for us because we know that before we start solving such a, in general, difficult cross-state recourse problem, we will generally first analyze the easy approximations, and they are indeed implemented in the software. So we can do that. Okay? Here we go. Let's first solve the easy approximation given by the expected value problem. That's just an LP. And I plugged in the numbers. And, well, of course, this solves in 0 time. It's a very small problem. And out comes an optimal solution. XEV. And these are the numbers. So the expectation is that the solution for our deterministic problem is to buy 32 units from country A and a bit more than 19 from country B. That's what comes out of the deterministic formulation, but we do know that the correct model actually captures uncertainty by random variables, and that's why we also will analyze it here. Further remark is, if you look at the deterministic EV problem, then it turns out that the recourse variables y, which are still there, are actually equal to 0. And that's an indication that the recourse is, well, even a bit more than sufficiently expensive. The recourse cost structure is such that in the deterministic setting you will use the recourse variables. That's a special case. It's always something that you should observe as being part of what you find out of this simple model. Okay, then we take that solution and see how it behaves in the true setting involving uncertainty. And then what we get is, of course, the same first stage cost. Well, that makes sense, it's the same solution. But on top of that, we get recourse cost. Quite a bit. So the total expected cost, the expected result of this EV solution, is substantially higher than the lower bound that comes out of that EV problem formulation. So that's one thing to observe. The gap between the upper bound and the lower bound is 22.6 units. That's talking about millions. Euros is probably realistic for this business. And also relatively, it's quite big, the gap. It's 18%, 18.5%. So from this very easy initial analysis, solving an LP in a single function evaluation, the message is, yeah, we probably should solve the recourse problem because, well, the true optimal value might correspond to a very different solution, bringing lower total expected cost. No lower than the lower bound, but maybe not quite as high as the upper bound that we just had. Okay? So now we are looking forward to solving our first recourse problem, and if we tell the software that this is what we're going to do, it shows you typically a list of available algorithms available in that software package you did. And for this problem, being a simple recourse problem with continuous distributions, there are 5 different algorithms. And again, you need your knowledge, which you do not have at this point, but next week or maybe the week after, we will talk about algorithms for recourse models, so then you know what those different algorithms stand for. And let me just tell you that it really matters. If you pick the right one, given that you know that it's simple recourse, it's probably a good idea to take a solver which has simple recourse in its name, SR, if you take that, it solves very quickly. If you choose less fortunately, it might take a bit of time. Yeah, so it's an important thing, and again, you need your knowledge to make the right choice. In fact, the solve that problem as given, but first make a discrete approximation for distribution. If you do so, turns out, instead of just 5 solvers, now there are 22 different solvers that you can pick to solve your recourse problem. And that makes it even more important that you know what you're doing. And to show that you cannot always just rely on the name of the solver, one of the solvers that then becomes available is MINO SLP, which is, by its name at least, a very suitable algorithm, right? In fact, it's not MINO SLP, it's MINO LP. It's just an LP solver. What it will do is solve that huge linear program and take virtually forever to do so. So making a bad choice here now comes at a price, namely your time. In fact, for a more realistically sized problem, it makes a difference between being able to solve it and not being able to solve it. Well, that's not within a year. So be informed that that's an important thing to do. Talking about coming up with a discrete distribution, since a couple of days you know how to do it. Remember, we talked about Jensen approximations to get a lower bound, the true optimal value. At the same time, Edmonds-Madansky approximations give you an upper bound. The good news is that the software can actually construct those Jensen approximations for you at the press of a button. You specify for each random variable how many realizations, how small or large the discrete approximation should be, and you press the button and it works. The bad news is, there's a Madansky approximation you have to use. Yeah? Okay, so that's all implemented in the software. And suppose that we pick the right solver corresponding to the particular recourse problem. We can solve, and in fact it's a trivial problem, so also solving the recourse problem in this case doesn't take any time at all. The last time I tried, it took almost no time, 0.03 seconds. So that's quick enough. And what do we get? We get the corresponding solution, that is the first stage solution. Again, indicating what should be the amounts that we buy from the countries. And I don't remember exactly the solution that came out of the deterministic formulation, but they're not the same. They're different numbers. And in particular, I think the amount we buy from country B increases from a bit more than 19 to 22. So it's a different solution. And that is also reflected in the optimal value for this recourse solution, namely the total costs are 133.6, comprising first stage costs, which have increased, but the second stage cost, the second term, relative to what we found in the EEV, has decreased substantially. So here we see that the solution that comes out of the recourse model actually balances the immediate cost versus the expected future cost, and it does so in a much better way than true. Indeed, the difference between what we get out of the two, we know, comes by the name of the value of the stochastic solution. That's the difference between that upper bound and the true optimal value, which is 11 million, or a bit more than 8% in relative terms. And we know how to give an interpretation, and in fact, I would ask you to always think about that interpretation in terms of the context of the problem. We're not going to go into that right now, but that's what you need to do when you look at those numbers.